Hey, how's it going? Welcome to part 2 on 13.5. This video we're just going to finish off looking at local and global maximum and minimum points. So essentially if we've got a curve, something like this, if we have a look at the point A, we can say that is a local max point. So it's a local max because the points around that point is going to be so point A is greater than those of its neighbours. So point A is a local maximum point. It's different to the point at C because not only is C a local maximum point because its y coordinates are greater than those around it, but it is also a global maximum point because it's greater than all other points on the graph. So it doesn't always occur. Not all graphs have a global maximum point. In this case, as you can see, the y values on C is greater than every other point on the curve. And it's basically exactly the same thing for minimum points. So this would be a local minimum. And this one doesn't have a global minimum point. But as you can see, if this went down like that, then this point here at F would be a global minimum point. So we're just going to look at some definitions here to start off with. So a function f of x has a global maximum f of a if all f of a is greater than or equal to f of x. A function has a global minimum if it's less than f of x for all x values. The function has a local maximum if the point is greater than points on f of x around the neighborhood, and same for the minimum. So it probably doesn't make much sense, but we'll have a look at an example 11. So a function defined on a restricted domain has the rule y equals x over 2 plus 2 over x for the x elements between 1/4 and 4. So specify the coordinates of the endpoints. So the endpoints is endpoints, subbing in x equals a quarter and x equals 4. And when we do that, we get y equal to 8 1/8, or 2 1/2. So there are coordinates of the endpoints. So I can say the endpoints are going to be 1/4, and if we make that into a improper fraction, we get those coordinates. So part B says obtain the coordinates of any stationary point and determine its nature. So stationary point is looking at the derivative. So if I find the derivative, I might just rearrange okay, just so the powers are a bit easier to work with. So we get 1 over 2 take away 2x to the minus 2 for our derivative. And when does that equal 0? So I say 1/2 take 2 over x squared is equal to 0. If I solve that, I get I get plus or minus 2. And I want x equals 2 because my x values are between my quarter and 4. So reject. So we reject x equals minus 2. So what happens at x equals 2? I get y equals 2 over 2 plus 2 over 2, so equals 2. So therefore 2 comma 2 is a stationary point. If I work out its nature, so at 2 and 1 either side, my derivative y dx is going to be 0 at the point 2. At the point 1, I get half, take 2 over 1, which is minus 3 over 2, and at 3 is 5 over 18. So we get negative, it's horizontal, positive, so it's a local minimum, so minimum turning point. Part C says sketch the graph of the function. We have no y-intercept because if we have a look back at our domain, it's between x is a quarter and 4. So we have no y-intercept. Because of the domain. There's no x-intercept since the endpoints and the minimum turning point all have positive y values. And minimum turning points have so if we have a look at our graph now, we worked out at the quarter we have the point 1/4 65 over 8. Our end point at 4 was 4 comma 5 over 2. We had a local or a minimum point at 2, which was 2, 2, and again just connecting the dots, something that looks like that. And the last part, part D, state the global maximum and the global minimum values of the function if they exist. So the function has a global maximum of 65 over 8. Being the left endpoint, and a global minimum of 2, 2. So that was part D. So that's 13.5 on curve sketching. Have a go at the questions. Thanks for watching.